Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to our course. It's a sunny day at Guwahati, but I am sitting inside an extremely cold recording room, and it's quite a bit uncomfortable to sit here. But we just have to continue our course, and so let us focus back to the second module of our MOOCs course on the fundamentals of nuclear power generation, where we are discussing about this very intriguing topic of radioactivity and nuclear reactions. In the first lecture on this particular topic, you were introduced to the term radioactivity, which was defined as the spontaneous decay of some unstable isotopes or nucleus, which led to the emission of several particles and also generally release of a good amount of energy. And this is a spontaneous reaction, because of which we have the process of transmutation happens, that is, one parent nucleus gets converted to a daughter nucleus. The daughter nucleus itself can also be radioactive in nature, leading to the formation of radioactive chains till the appearance of some kind of stable isotopes or stable nucleus. And this disintegration of such radioisotopes is governed by such an exponential relationship, which we have derived during our last lecture. Here N naught refers to the number of isotopes present at the beginning of some chosen interval, where lambda is called the decay constant. Lambda is a characteristic of the radioactive particle itself or radioactive isotope itself, but a more important property which is extremely important to know about any radioactive isotope is called the half life, which is defined as the time required for the number of nuclei present in a sample to reduce to the half of its original value. And this half life is related to the decay coefficient or decay constant by this simple linear relationship, or you can say the half life is inversely proportional to the decay constant. Now, half life is a very important parameter for any radioisotope, because each isotope has its unique value of half life, and the unit of half life of course is time, but it has a very wide range to cover. For some isotopes it can be in the range of seconds, or even sometimes even less than seconds, whereas for certain other isotopes it can be in the range of a few billion years. Like very common isotopes like uranium 238 or thorium 232 have extremely long half life, which is the reason for them still existing in the universe. But as half life is a unique parameter for any radioisotope, so decay constant also has to be a unique parameter. That means, for a given radioisotope the value of decay constant also is a constant, and I should also say it is unique, means two radioisotopes can't have the same value of the half life and therefore same value of the decay constant. Now, we know that the unit of half life is time, because we are talking about a time span. Then what should be the unit for this decay constant, as they are inversely proportional to each other? So, the decay constant, where the half life its unit is time, so the decay constant must have its units as time inverse. So, depending on what kind of material we are talking about, we can use second inverse or minute inverse or even larger units to specify the value of decay constant. After knowing about these properties like decay constants, half life, mean life, etc., you were introduced to some radioactive calculations, where it took a very simple relation or simple binary reaction from some parent isotope A converting to some daughter isotope B, and by solving their mathematical forms we have seen that their number of nucleus will show a simple exponential relationships such as this, where A will decrease exponentially and correspondingly B will increase exponentially. But in real life we never get such kind of binary reaction, rather we are always present with radioactive chains, that is a chain of reactions starting from some heavy nucleus in general, and then going through several intermediate or daughter nucleus, and still the final formation of some kind of stable isotopes. Like the example of uranium-235 decay chain, which was presented earlier also, where we are starting with uranium-238 and finishing upon with lead-206, this Pb-206, which is a stable isotope. Basically, it is non-radioactive, and then only we can have this chain complete, but in between you can see there are a large number of intermediate particles. In fact, there are other isotopes of lead as well, which are radioactive in nature, but this Pb-206, which is the final product, is non-radioactive, and therefore, that is where the chain ends. So, today we have to see how to analyze such kind of decay chain, and then we shall be moving to study different kinds of radioactive reactions that are possible. Now, if we talk about any of the intermediate nucleus that can appear somewhere between the radioactive chains, we can always write a conservation for the corresponding nucleus as the time rate of change equal to rate of generation minus rate of decay, or mathematically d and dt is equal to g minus lambda n, where n is the number of nucleus for that particular species that we are talking about, g is the rate of generation, and lambda is the corresponding decay coefficient. So, the rate of decay will be given by lambda into n as per the decay law. And mathematically solving this ordinary differential equation, we can get a solution of this particular form, assuming of course, the initial number of this intermediate nucleus to be 0. Now, you can see here we have an 1 minus e to the power minus lambda t term inside the bracket. If we are talking over a very large time scale, like when t tends to infinity, or means infinite time refers to certain time which is much bigger compared to or corresponding to the time that is important from our phenomenal point of view. Like say, if we are talking about if your zone of interest or period of interest for a certain activity is only say 1 second, then even 20 seconds can also be treated as infinite. And therefore, this exponential term over a very long time interval of course tends to 0 or becomes negligible, yielding this n t is equal to g by lambda. This is particularly true when you are talking about an element with extremely long half life, like U-238 or TH-232. Extremely long half life means extremely small value of lambda as well, and because of their such long life, their and slow rate of decay, their number of nucleus changes extremely slowly, and therefore, the generation rate of their respective daughters and descendants remains virtually constant, because the rate of generation of their daughters will be given as just the same as for this uranium-238, where n into lambda is a constant, and n will change very small by very small amount over a reasonable period of time, and therefore, g will become equal to the activity of that U-238 or whatever parent nucleus we are starting with. This kind of situation is called secular equilibrium. This one we shall be coming back to after a little bit of mathematical exercise. Now, let us take a very small radioactive chain which involves not 2, but now we have 3 elements. A is the initial parent which is decaying following a rate of lambda to some daughter isotope B, but that also is radioactive in nature. So, it is also decaying to an isotope C following another coefficient lambda B. So, let us write the conservation equations for each of them. First, for element A, as there is no source for generation of A, it can only go through the decay, and therefore, we get this particular equation. B of course can get generated because of decay of A, and it is also getting decayed or disintegrated and getting converted to C. Accordingly, the conservation equation for B can be written like this: rate of change of B nucleus will be equal to lambda A n A, which is the rate of generation, and also the rate of decay of A. Similarly, the rate of decay of B is lambda B into n B, and the balance between these two terms will give you the rate of change of A isotope. And finally, the species C, where there is only generation, but no further decay, as in this elementary chain we are considering C to be a stable isotope, and accordingly we get this particular rate of equations. Now, these three are the all three of them are single order or first order ordinary differential equations which require simultaneous solutions. but we have another condition here. At any time instant we can say that time rate of change of the total number of isotopes present in the sample will remain constant. That is quite straightforward, because disintegration of one isotope of A will produce only a single isotope of B, and similarly a disintegration of a single isotope of B can produce only a single isotope of C, and therefore total number of isotopes in the sample has to remain the same. Now we can solve these equations. Solving the first ODE with an initial condition of Na equal to Na naught at time t equal to 0, we get the familiar exponential decay form of the element A. For the B, let us put this expression of Na back to B, and so now we have after rearranging the terms, dNB dt is plus lambda B NB is equal to lambda A into Na, and so that this is the Na part which has been replaced by the form just we got in the previous line. Now we multiply both sides of the equation, that is both the right hand side and left hand side, with e to the power lambda b t, and accordingly I am multiplying both sides of this equation with e to the power lambda b t, which can be treated as a the integrating factor in this particular situation, and accordingly we arrive at this. We can write the right hand side as the time rate of change of this product of N b into e to the power lambda b t, and left hand side of the left hand side we can write as the time rate of change of this product of N b and e to the power lambda b t, and right hand side is a straightforward form, and this can be integrated from time t equal to 0 to whatever time t we want, taking N b equal to N b naught as the initial concentration of B or initial number of nucleus of B, and accordingly we get this particular mathematical form of N b. This is simple mathematical derivation you can derive following the procedure that I have just mentioned, and then making use of this particular condition we can get the number of nucleus for N c variation with time. So, we have the mathematical solutions for N a, N b and N c, and if we combine all three into a single graph, we are going to get a form like this, where A continuously decreases because it is not having any kind of source, whereas N c continuously increasing following the green line as it is not decaying anymore, but B is having both a source and also it is getting decayed. Accordingly, its rate initially increases, but then after reaching certain maxima it starts to decrease. This location of this maxima of this element B or isotope B, which seems to be somewhere here, is it presents a very interesting optimization problem. While drawing these graphs, we have assumed N a to be 1 and N b and N c to be 0 in the initial sample. Lambda a has been taken to be 0.5, whereas lambda b is taken as 1. Now, this optimization problem, we can identify the location of the maximum number of nucleus of B and the corresponding time by setting d n b dt equal to 0, and accordingly I have written here the final solution where we have the expression for the optimum time t. Basically, we are referring to a time somewhere here which corresponds to the maxima of this B nucleus. You can clearly see that it depends only upon the two decay coefficients N a and N b, and lambda a and lambda b, and also it depends upon the initial concentration of A and B, both isotopes. Now, we can have several situations in this case. For the set of numbers that we have here, the T optima is coming to be 1.386, and also it is interesting to note that the maximum concentration or maximum number of nucleus for B is just over 0.2 for this particular combination of parameters. Now, we can have several cases here. I have reproduced the expression for N b just for easy reference. So, first situation can be when lambda b is greater than lambda a, that means the isotope B is getting decayed at a rate higher than the isotope A. So, if we put that in the mathematical expression, after some reasonable period of time, the exponential of minus lambda b t will be extremely small compared to exponential of minus lambda a t, and accordingly the expression for N b reduces to this particular form, finally yielding N b upon N a is equal to lambda a by lambda b minus lambda a, which is definitely a constant. because please remember lambda A and lambda B both are uniques to the elements A and B respectively, and both of them are constants for the corresponding isotopes, and therefore, this particular ratio of lambda A minus lambda B, lambda A divided by lambda B minus lambda A has to be a constant whose value can be evaluated if we know the magnitude of lambda A and lambda B both. And accordingly, we can see that we can conclude that the ratio of the number of nucleus of B and A after some period of this combined decay becomes a constant. This particular condition is known as transient equilibrium, and this is something that we can always find in practice. Like if we see the same graph that was present in the previous slide, you can see from some time somewhere here Na and Nb are basically these two lines are overlapping with each other, because if you remember here while drawing these curves we have considered lambda A to be equal to 0.5 and lambda B to be equal to 1. Therefore, this particular ratio lambda A upon lambda B minus lambda in this case is equal to 1. That means, the number of isotopes of A and isotopes of B, they will remain the same. It does not mean that Na and Nb are becoming constant, rather the rate at which Na is going to change, the same rate Nb is also going to change after some initial period of development, which has been found here. Putting different values of lambda A and lambda B, we can get different slopes for this curve, but the ultimate conclusion is whenever lambda B is greater than lambda A after some period of initial development, the ratio of the nucleus will become equal to a constant. Now, we have the second situation where lambda B is less than lambda A. Again after some period of initial development, now the exponential of minus lambda A t becomes negligible. Accordingly, we get this particular expression of Nb, and corresponding graph is this, which has been plotted considering lambda A to be 1 and lambda B to be 0.5. Nature is more or less similar, but interesting to observe here that the maxima in B is much larger, more at least double compared to the previous situation, and that can be understood from our senses, because here lambda A is greater. So, the rate of production of A is definitely larger compared to the rate of decay, at least during the initial period when the constant number of A nucleus is quite high. But once we reach this particular zone, now number of A nucleus is quite small. So, despite lambda A being large, the generation rate of the isotope B keeps on reducing, giving an overall decaying profile of this isotope B, but C as usual keeps on increasing continuously. And now, the very interesting situation where we can have lambda A and lambda B to be equal to each other. Now, the previous mathematical expression we can't apply here, because that will lead us to a 0 by 0 kind of situation. Rather, we can go back to the earlier balance equation to write something like this, and we can straight away solve this again by multiplying both sides with e to the power lambda B t. We get this particular form, and finally, the corresponding expression of Nb as something like this. So, if we represent graphically, this is the graphical form that we are getting, which has been plotted considering both lambda A and lambda B to be equal to 1. In this case, again the maxima is somewhere in between the previous two cases, that is expected, and here the optimum time will have a different expression, which we can again obtain by maximizing this particular function Nb, and that will come to be lambda B inverse. Here for the given combinations of lambda A and lambda B, this is coming to be equal to 1. I would urge you to develop this particular mathematical form, that is a just straightforward differentiation of this particular expression with respect to time and setting up to 0, which should lead to the T optimum of lambda B inverse to the power minus 1. Now, we have a special case when lambda B is much greater than lambda A. If we put these numbers through the expression, original expression for lambda B, after some period of initial growth, e to the power minus lambda B t tends to 0, and accordingly we have this mathematical development of lambda B n B is equal to lambda A n A, or activity of B to be equal to activity of A. This is a very important relation. This is what we call the secular equilibrium, which I have mentioned couple of slides back. The isotope B quickly attains the same activity level as of A due to its much larger rate of decay. Like if we see that graphically, here we have the same three lines. The red one corresponds to Na, and the blue one, which is hardly visible, which is hiding somewhere here, it is Nb, the green one is Nc. Because the rate of decay of B is much larger, while plotting this we have used lambda A equal to 1 and lambda B to be equal to 40. The B nucleus is getting decayed as soon as its generation. Initially A isotope being very large, that is why it appears for a very short period somewhere here, but after that it starts getting decayed at a very fast rate, and therefore, we can hardly see B. It can be almost assumed that the A is getting converted nearly directly to the isotope C. In this case, the time optimum comes to be 0.094, which is extremely small. And therefore, whenever we are talking about very large difference in the activity level, or I should say the decay constants values for two isotopes, particularly when the daughter isotope is having much higher rate of decay compared to the parent, then the daughter itself may almost vanish from the picture and lead to say similar activity level for both the parent and daughter. So, that secular equilibrium condition we can very safely use whenever you are talking about an isotope. So, with a daughter isotope with extremely small or extremely large decay constant or extremely small half life. Like for parents U238 and TH232, they have very large half life and therefore extremely small decay constant. So, invariably their daughters will have much larger decay constant compared to them, leading to the appearance of this secular equilibrium. So, we have discussed a bit about mathematics so far. Let us now come back to the phenomenon of radioactivity. Now, radioactivity or corresponding transmutation is a phenomenon that was first achieved in the laboratory scale by Rutherford in 1919, when he bombarded his nitrogen nucleus, some nitrogen nucleus with high velocity alpha particles, and that resulted in conversion to oxygen and also release of proton. Actually, this is the experiment by virtue of which he proved the existence of protons as well, but this particular nuclear reaction is given by this famous form, where we have nitrogen and helium nucleus, which is the alpha particle as was mentioned in the previous lecture, and on the right hand side we have an isotope of oxygen O17 plus proton. This is first you can say the first man made or human controlled transmutation reaction that was reported or that has been reported. Of course, everything was still not controlled by that time, but still it was done at the laboratory scale, and therefore, this can be considered to be a pioneering experiment in case of the transmutation phenomenon. And another point to note here, that here Rutherford used helium nucleus, that is alpha particle, to break apart the nitrogen nucleus. Now, alpha particle, if you remember carefully, they comprises of 2 neutrons and 2 protons. Therefore, they are also positively charged. They are having 2 units of positive charge. Now, we are trying to break the nitrogen nucleus, where we are having 7 number of proton and 7 number of neutrons. So, that is also quite strong, that is also carrying strong amount of positive charge. We are trying to break that with another very positively charged particle, and hence as the alpha particle approaches this nucleus, it will be facing large amount of repulsion force because of their identical sense of their charge, and therefore, this particular reaction, that is the alpha particle breaking the nitrogen nucleus, is possible only when the alpha particle has very high kinetic energy of the order of several millivolts. Then only it is able to penetrate into the nucleus of nitrogen and cause this reaction. But one thing to point out here, this is not the only kind of nuclear reaction that is possible. There are several kinds of nuclear reaction possible, which we shall be discussing in the subsequent slides, but which kind of reaction that is going to take place in a particular situation depends upon mostly upon 2 factors. One, the configuration of the nucleus itself, or I should say the number of nucleon present in the nucleus, and second, the ratio of the number of neutrons to protons. Both are related to the configuration of the nucleus, and for a given nucleus both of them are generally known phenomenon, and standing at present time we can more or less predict what kind of reaction one particular nucleus is going to have just by knowing the number of nucleons present there, and also the second one very important, the ratio of the number of neutrons and protons. This is something called the nuclear shell model. Now, we are not going to enter into the detail of nuclear physics because that is far beyond our scope, but just for your information, there are several theories of the structure of a nucleus, and nuclear shell model is a very popular theory of there, which postulates that the neutrons and protons, basically the nucleons, are placed in several oscillating cells inside the nucleus, quite similar to the electrons in the outer orbits. But the interesting thing is the last column here, something called the magic number. The magic number refers to a certain number of nucleons present in certain orbits, or I should say when the total number of nucleons are any of these numbers mentioned here, that is starting from 2 going to 8, 20, 28, 50, 82 and 126, then that corresponding nucleus will be a highly stable one. I repeat, a nucleus is having any of this number of nucleons in its nucleus, it is expected to be highly stable as per the nuclear shell model. But of course, this is a very restricted case, and most of the practical isotopes are not having nucleons equal to the magic number, and therefore, they are vulnerable from this point of view. And then comes the second factor, which is the ratio of the number of neutrons and protons. Now, look at what we have here. Here we are trying to compare 5 different isotopes of carbon. Being carbon, all of them are having 6 protons in their nucleus, but the number of neutrons vary. The first one is C11, where we have only 5 neutrons, and the last one is C15, where we have as many as 9 neutrons. And it has been found that while 6C12 and 6C13 are very stable from nuclear reaction point of view, 6C12 having equal number of neutrons and protons, so a ratio of 1, whereas 6C13 is having just 1 neutron more than the proton, and so N by Z ratio of 1.17. Both of them are highly stable from radioactivity point of view. But when we go to a low value of N by Z, like for 6C11, where there are 5 neutrons, so giving an N by Z value of 0.83, or when we go to the territory of large N by Z ratio, like for 6C14 or 6C15, 6C15 has 6 protons and 9 neutrons, giving an N by Z ratio of 1.5. Both these two situations are generally quite unstable from nuclear reaction point of view. Therefore, we can conclude that, and not only from this, by considering several other isotopes that we can found in nature, any N by Z value just at 1 or slightly above 1 is quite stable, but N by Z value less than 1 or much higher than 1 generally leads to some kind of unstable nucleus. This is one graphical representation, again a phenomenological observation, where this particular line is the N by Z equal to 1 line, that is equal number of neutrons and protons present in the nucleus, and the orange band that is shown just on top of that, that is stable band. So, the nucleus which are having N by Z ratio lying within this band, they are generally quite stable from nuclear reaction point of view, but anything lying outside that orange band is expected to be unstable. So, for low value of atomic number, that is up to something like this range of atomic number of 30, 28, around that, we can see more or less N by Z equal to 1 is the condition for stability, but as we go to heavier elements, N by Z ratio keeps on increasing, and generally for an Z value of 80, the corresponding stable limit, as we can see particularly for this isotope of mercury 80 Hg200, where we have 80 protons and 200 neutrons, giving a ratio of 1.5. As we keep on, that is also stable. That means, as the atomic number keeps on increasing, the stable value corresponding, or the N by Z ratio value corresponding to the stable nucleus, that also keeps on increasing and reaches around 1.5 for such heavy nucleus. but the nucleus which are lying outside this band, they try to go through some kind of nuclear reaction which allows them to come back within this band, and accordingly we can find several kinds of nuclear reaction like shown here. Just similar graph, but instead of that orange band we are having more a brown colored line here. So, the elements which are having n by z ratio higher than this, that is more neutrons compared to the protons required for the element to be stable, they are beta emitters, or they go through the beta decay kind of reactions, whereas the elements which are having low n by z ratio, that is they have more protons compared to the number of neutrons, they go through a beta positive emission or positron emission. We shall be coming to this shortly, and only for heavy isotopes, that is when the atomic number is 80 or even higher, we can have the alpha decay or emission of alpha particles. So, we can clearly see there are at least 3 kinds of nuclear reaction possible as per this particular curve. One thing we have to keep in mind, that when you are talking about a very light isotope, n by z equal to 1 is sufficient, but when you go to heavy isotopes, the stable band corresponds to a higher value of n by z, can be around 1.5. That can be, that we can understand by considering the presence of more number of protons. As the number of proton keeps on increasing, their repulsive force also keeps on increasing, and to counter that repulsive force we need to have sufficient amount of binding energy present in the nucleus, and that can be present only by adding more and more neutrons into this. But of course, even more number of neutrons than required will again lead to an unstable situations. So, depending upon whether the n by z ratio is higher than required or lower than required, we can have 2 different kinds of radioactive reactions. And of course, we can also have alpha reactions or alpha decay, which is generally followed or identified for heavier isotopes only. So, this is alpha decay, which is primarily relevant for nuclei with z greater than 80, but that does not mean that it does not happen below z for z less than 80, but it is more prevalent when z is greater than 80. This is an example of that. A parent nucleus, in this example we have uranium 238. Alpha decay means very stable helium isotope, that is 2He4, which is going out, and because of that we have a transmutation process where we have a daughter isotope forming with 2 protons and 2 neutrons less than the original one. It can be represented in a form like this, which we have seen in the last one also. If the parent is having z number of protons and a number of a minus z number of neutrons, then the daughter will be having z minus 2 number of protons and a minus z minus 2 number of neutrons, giving a mass number of a minus 4, plus of course the helium. So, a helium decay leads to the reduction in z by 2, because 2 protons are going out, reduction in the number of neutrons by 2, because again 2 number of neutrons are also going out to the helium, and therefore, a total reduction of 4 in the mass number of this daughter isotope. Here are some examples related to heavy nucleus. We have plutonium 239 undergoing alpha decay to form uranium 235, something a very common reaction in nuclear power plants. Similarly, another common reaction U235 going through a alpha decay and forming TH231, and a few others. There are a couple more examples which are for isotopes less than 80, and they lie in the group of rare earth materials, where we have Nd144 going through an alpha decay to produce C140, and another hafnium of 174 producing Yb170. And some very interesting example in this particular group here for extremely light isotopes, which are generally not associated with alpha decay, but what we can see here, the first one is another isotope of helium itself, helium 5, which can release one neutron and thereby gets converted to a helium 4 isotope. So, we can visualize this in either way. We can either call this an alpha decay, or we can also this as release of a neutron. Lithium 3Li5 is again going through a process where we are getting a proton and a helium. So, it can also be talked about either as an alpha decay or a proton separation. And the last one is a very interesting example of 4B8, Here beryllium is going through alpha decay process to produce not one but 2 alpha particles, that is 2 helium isotopes. But we definitely have such examples listed here in the second and third column, but more practicables are the one presented at the left, that is relevant to the isotopes having a mass number of 80 or greater than that. Now, I come to the beta decay. Beta decay is relevant to any kind of nucleus, heavy or light, but those which are having a high n to z, n by z ratio. As a beta decay happens, like on example shown here, here we have 6C14. So, 6C14 as mentioned in the previous slide, here we have 6 carbon, in this carbon isotope we have 6 protons and 8 neutrons. So, the ratio of neutron to proton is 8 by 6, which is quite high, and therefore, it goes through a beta decay process, means it releases one electron from the nucleus and gets converted to a 7N14 isotope. And this particular isotope of nitrogen is having now 7 proton and 7 neutron. So, it is n by z ratio of 1 and perfectly fine from nuclear reaction point of view. This can be the corresponding form for the general reaction, where the parent is having Z as the atomic number and A as mass number, as we are having a mass -1 loss in the atomic number point of view. So, the daughter will be having a Z plus 1 as the atomic number, and A, the mass number remains unchanged. Accordingly, we can summarize the beta decay as an increase of 1 in the atomic number and decrease of 1 in the number of neutrons, so that the total atomic number remains unchanged. These are certain examples ranging from very light to very heavy elements, 6C14 going through a beta decay process, and whenever you are having 6C14, whenever you are having a beta decay, you have to remember that the daughter will be having 1 proton more. So, 6C14 will produce something which is having atomic number of 7, that is nitrogen, and mass number will remain unaltered. So, on the right hand side we have 7 and nitrogen plus the electron. Similarly, we have 3 other reactions. These are Fu for the heavier nucleus like U235, TH234 or radium 228, like the middle one may be the thorium 234 going through a beta decay to produce Pa90 234, which is having 91 protons in it. But it is quite interesting to think that the nucleus is consisting of protons and neutrons, and there are no electrons inside the nucleus. Then how a nucleus can release beta particles or electrons? That is a very puzzling question. The answer lies here, means the beta decay can be viewed as a conversion of one. You have to think about which particle or which element is more in the nucleus. Of course, neutron is more. So, the beta decay can be thought about a process of reducing the number of neutrons and increasing the number of protons, and which can be achieved by converting one neutron to a proton and an electron, such an element like this. So, as the neutron gets converted to a proton and an electron, its mass will be carried by the proton, and neutron is electrically neutral, but the proton, that is the two products here, the proton is having +1 charge and electron is having -1 charge. So, that also remains balanced. But one issue is that the mass of proton, neutron and electrons all were given in our module 1. If you put all of them here, you will find there is a significant amount of mass defect. And another factor that has been observed, that during beta decay, the momentum distribution, energy distribution that we get, they are very regular curves showing distributions like this, which is not true for other kind of radioactive decays. Like for in case of alpha decay, we get several bands with different amount of energy levels, and this, therefore, this kind of behavior violates the conservation of energy and also violates the conservation of angular momentum, and therefore, there must be something else which also is happening along with this beta decay. That was first postulated by Pauli, who identified a particle which was named neutron that time, that this is also accompanying the ejected electron. It is electrically neutral and its mass is extremely small, of the order of 10 to the minus AMU compared to even electron also. And then if we consider the presence of this neutrino and also the amount of energy released during the beta decay process, then we can get a balance between the mass and momentum conservation. and of course energy conservation as well. So, the general expression or general mathematical form for beta decay should not be the previous one, rather this should be the correct form, where this parent ZAPA is leading to the formation of a daughter plus one electron or the beta particle, plus this is something earlier used to be called neutrino, but now it is called anti-neutrino, where the term anti has been assumed in showing respect to the presence of the electrons, and neutrinos being the anti-particle of these electrons. Here we have two zeros along with this neutrino, which represents its mass is 0 as well as its charge is 0. And following the Pauli's postulates, the theory of Fermi established the concept of beta decay properly. It is a very comprehensive or exhaustive statistical development, but we are just taking the gist from there, which says that firstly the electrons and antineutrinos can be created or annihilated during any such kind of beta decay process. Secondly, protons and neutrons should be considered as two internal quantum of states of a single particle type, which is nucleons. Basically, again from nuclear physics point of view, both types of nucleons comprises of quarks. There can be two types of quarks, the up quarks and the down quarks. The up quark comprises of plus or carries plus 2/3 element of charge, whereas the down quark carries minus 1/3 element of charge. When you are talking about a proton has two up quarks and one down quark in its structure, which gives a total charge of 1 unit to a proton. Whereas, when you talk about a neutron, for a neutron we have 1 unit of up quark and 2 units of down quarks, giving it a total charge of 0 or making it electrically neutral. Therefore, just by conversion of this up quark to down quark or down quark to up quark, we can convert neutron to proton or proton to neutron, and hence they should be treated as a similar kind of particle. And the third point that we can get from Fermi's theory is that every transformation of a neutron into a proton must be accompanied by the creation of an electron and an antineutron. Similarly, when you are having the reverse process, that is a proton is getting converted to neutron, that also must be associated with the appearance of a positron, which is the opposite particle or of electron, and a neutrino, or it can also correspond to the disappearance of one electron and the antineutrinos. And this now should be the correct way of representing beta decay. Here we have the nitrogen, which is getting broken into not 2 but into 3 components now. The first one is proton, second one is electron, that is the beta particle, and finally this is the new one, that is a neutrino, it is, or I should say antineutrino, that is coming into the picture. The rate of this reaction is given by something known as the Fermi's golden rule, where on the left hand side we have this lambda, which is called the probability of transition from the initial state before decay to the final state after decay. Here rho f at the end is the density of the final state, and m represents the coupling between the initial and final state, and the h bar here is a Planck constant divided by 2 pi. Now, beta decay is definitely the most common phenomenon that we can find in different nuclear reactions, but there is a counter of that, that is called the beta plus decay and also called the positron decay. Positron is an antiparticle of electron, which is having the mass of the same amount as of electron and same magnitude of charge, but of opposite sense. That is, a positron can be viewed to carry plus 1 amount of electrical charge, but its mass is as the same as of electron. So, positron decay or beta plus decay are associated with elements, just it is the opposite situation of beta minus decay or beta decay. The normal beta decay is associated with isotopes having high n by z ratio. So, the beta plus decay is associated with nucleuses having a low n by z ratio. Here a proton gets converted to neutron, and also the electrons, or I should say the positrons and the neutrinos. So, this is the general for mathematical form we can write. Here the parent is having z number of protons and a minus z number of electrons. Number of electrons remains as it is, or I should say a minus z number of neutrons. Now, because of this nuclear reaction, total number of nucleons remains the same, that is a. but total number of protons reduces by 1. So, the daughter is having Z minus 1 as its atomic number, plus we have a positron. So, by beta decay it is the opposite situation of electron decay or beta decay. This positron decay is associated with increase in Z by decrease in Z by 1, increase in n by 1 with the mass number, that is A, remaining unchanged. We are just going back to the diagram just to point out whatever we are discussing here. This is dotted line you can which you can see here, this is the band of stability. So, when we are talking about the beta emission or electron emission or beta minus emission often called, we are associated with, that is associated with isotopes having a large n by Z ratio. So, we are into this zone where isotopes are having more number of neutrons compared to proton than required, whereas this positron decay is relevant to this particular situation where the particles are having less number of neutrons or they are having excess protons compared to whatever required to have a balanced situation. These are some examples like 7n13 going to a positron decay to form a 6c13 plus positron plus neutrinos, and there are a few other examples given on this slide. But one interesting situation is that whenever we have a positron decay, the number of protons has as we have seen in the previous slide, the number of protons has gone down by 1 and one positron has come out of the nucleus. But what happens to the positron then? And also let me go back once more. Let us talk about this particular situation. Here initially we are having a nitrogen 13 isotope which is having 7 protons and 6 neutrons in its nucleus, and to make it electrically neutral, of course, we are also having 7 electrons in the outside orbits. Now, after the reaction is done, we are having this particular isotope 6c13, which because of the conversion of one proton to a neutron, it is now having 6 number of protons and 7 number of neutrons in its nucleus. So, total number of nucleons remains to be 13 and the positron has come out, but in the outer orbits we are still having 7 number of electrons, and if this electron stays there, that will make the entire atom electrically negative. But the positron that is carrying a positive charge, that is coming out. So, the positron generally collides with the orbital electrons, and both the orbital electron and the positron emitted by the nucleus gets annihilated by the process, leading to complete conversion of mass to energy. And because of that, the daughter nucleus is also able to remain electrically neutral. So, this reaction can be written like this, where we have the positron first, which is coming out of the nucleus because of this beta plus decay, and then we have the electron from the orbits, both getting annihilated and forming 2 photons of this gamma reaction or gamma radiation. Now, as mass is getting converted to energy, of course, that will be associated with large amount of energy release, and we know that both electron and positrons are having same amount of mass. So, if we use E equal to mc square, then this particular reaction corresponds to an amount of energy release of 1.022 MeV. So, it is very important to note, just having more number of protons or excess number of protons is not sufficient for an isotope to go through positron decay. Rather, it must be at an energy level which is at least 1.022 MeV higher than the base level, then only it is possible to have the positron decay. I repeat, the parent nucleus must have this 1.022 MeV of energy, then only it can go through the positron decay process. But what will happen when an isotope is having excess proton, but it is not having this amount of energy? Then we have the other kind of reaction, that is called the electron capture, often called the K capture or L capture. It is an extremely interesting kind of reaction. Here the nucleus is having excess proton, but it is not having enough amount of energy so that it can go through a positron decay. Then it captures one electron from the nearest orbit. One of the electrons from the orbit, generally the K shell, sometimes from the L shell, that is dragged back to the electron, and now that electron combines with one of the proton that is present inside the nucleus, leading to the formation of one neutron and also one neutrino. So, the mathematical form will remain like this, where an isotope of ZAP is reacting with one electron. Mind you, this electron is coming from the orbits, leading to the formation of this daughter, which looks very similar to what we had in case of positron decay plus neutrino. But you have to keep in mind here, in case of previous case, we are having a positron coming out of the nucleus, and during that time a proton is getting converted to neutron. Here also with electron capture also proton is getting converted to neutron, but no positron is coming out, rather the antiparticular positron, that is an electron, is getting consumed by the nucleus. And once the electron from the K shell or L shell is consumed, another orbital electron which is rotating at some higher orbits will fall back to this orbit, and and go to a much lower energy level. So, the excess energy that this electron is carrying, that will be released to the surrounding in the form of X-rays. So, we know similar to the positron decay, during electron capture also Z is decreasing by 1, that is number of protons is decreasing by 1, but total number of nucleons are remaining unchanged because number of neutrons has increased by 1. These are some examples of starting with 13Al26, which is consuming one orbital electron and getting converted to 12 Mg26, and we can have other several reactions involving potassium 40, nickel 59, barium 128 here, and quite a few other reactions as well. And so, you have to keep in mind the difference between the positron decay and the electron capture. In both cases, we are having conversion of one proton to one neutron. In both cases, we are starting with a nucleus which is having excess number of protons, and so it wants to convert one proton to a neutron. In both cases, we are finishing up with a neutron, a daughter nucleus, which is having more number of neutrons compared to the parent. But in case of the positron decay, the isotope or the nucleus is having good amount of energy, at least something more than 1.022 MeV, and therefore, it is able to convert one proton to a neutron and eject one positron during the process. Whereas, in case of electron capture, the isotope is not having that much of energy, and therefore, it is drawing one orbital electron into its nucleus and combining that with a proton to get a neutron as a final product. All these three kinds of phenomena that we have discussed, beta decay, positron decay and electron captures, generally fall under the category of beta decay. And therefore, in several books and materials, you will also find that beta decay can be of three types, that is beta minus decay or the conventional beta decay, beta plus decay or the positron decay, and this electron capture or K capture. And the final one that we have is the gamma emission. Gamma rays are electromagnetic waves of very high frequency or very extremely small wavelength. So, gamma radiation generally is associated with all the reactions that we have discussed so far. Whenever we have a daughter nucleus formation, that is generally at a very excited state, and therefore, it releases that extra amount of energy in the form of gamma rays and comes to more level state or more ground state. Like the example here, 2760 cobalt is going through a beta decay process leading to the formation of this particular nickel 60 isotope, but that is at a very excited level. So, that goes through two levels of gamma radiation. In the first level, it releases one gamma photon and 1.1732 MeV of energy. In the second step, it releases another gamma photon and 1.3325 MeV of energy, and following these two steps, it is able to come back to the ground state. So, by virtue of this gamma emission, we basically are having isomar formation. If you remember at the beginning of this module, I mentioned about those terms isobar and isomar. Isomers are those which are having the same atomic number and mass number and number of neutrons, but their differences only in terms of energy level, and gamma emission corresponds to that. Gamma rays are electromagnetic waves of extremely small wavelength. It is the smallest among all of them. Like you can see here, we are talking about 0.01 nanometer and lower than that, where the zone of domain of gamma ray starts. So, it is much smaller than X-rays also from wavelength point of view. Therefore, there as such kind of photons are having the energy of such photons are proportional to their frequencies using, and we can calculate that as E equal to h into nu. So, gamma rays are carry extremely strong amount of energy. So, their radiation point of view, they are very much hazardous, and also they can penetrate virtually through almost everything. Whereas alpha particles are heavy and they can be stopped by very small obstacles like a piece of paper. Beta rays are they are much smaller, so they have more penetrating power compared to alpha particles, but the gamma, that is nothing compared to the gamma rays. And another important point, another important difference that we are having between gamma emission and the electron capture that we are having in the previous case. If you remember carefully, I have mentioned after the electron capture is done by the nucleus, one electron from the higher orbit falls back to the K shell to fill up the void, and during that the excess energy of that electron falling back from the higher orbit is released in the form of X-rays. Whereas, in case of gamma emission, an excited nucleus is falling back to its ground level by gamma emission, and that is a big difference between X-rays and gamma emission. Gamma rays originate from the nucleus, whereas X-rays are emitted by the electrons. Earlier days, the difference between gamma rays and X-rays were drawn more in terms of the wavelengths, but nowadays we go more for this particular difference. Nucleus is the place from where the gamma rays are originated, whereas whenever you have some radiation that is coming only from the orbits or from the orbital electron movements, that has to be X-rays. So, we have seen different kinds of nuclear reactions. But interesting thing to observe there, I am going back to the thorium-232 decay chain that we have seen earlier. You just look at here a radium-228 is going through a beta decay process, whereas later in this chain here radium-224 is going through an alpha decay process. That is, radium, of course, there are two isotopes we are talking about, can undergo different kinds of decay process. Here we have another one. Now, instead of different isotopes, we are basically having the same isotope of uranium-235 only, and depending upon the condition, it can have all the three: alpha decay, beta decay, or gamma radiation from some excited states. Here I have another example. The cobalt-53, it can either go through a reaction which produces iron-52 and releases a proton, or it can go through a positron decay process producing iron-53. That means, the same isotope under different condition can go through different kinds of nuclear reactions, and therefore, these new conditions that needs to be properly judged upon, and there has to be some kind of properties of these isotopes as well, which governs exactly what kind of nuclear reactions a particular isotope is going to happen. Finally, before closing, a few other nuclear transmutations that are also present along with this alpha, beta or gamma decays. The neutron emission is very common for nucleus with excess neutrons, particularly at the heavier nucleus and also at a very high energy level. It changes only the mass number, atomic number remains the same. Like in the first example, beryllium-13 is releasing one neutron and getting converted to beryllium-12. So, just another isotope of the same element. Couple of other examples here. Some very rare case, we can also have proton emission, like in this example of nitrogen-11 ejecting one proton and getting converted to carbon-10. If you add a couple of other examples which you can check out, and a very interesting one where we are actually starting with a mercury isotope and striking that with a neutron, and getting at the result we are getting gold 198 plus 1 proton. This is something that was the dream for the alchemist, to produce mercury from gold, and by virtue of this transmutation which we can control nowadays, this is definitely possible. So, the last one of course is the conventional fission reaction. Couple of examples I have given here, but we shall be discussing more about this in a later module. So, the gist here is that a nuclear and radioactive isotope can go through different kinds of nuclear reactions, but exactly what kind of reactions it can go through depends upon several factors, and also several properties or characteristics of the isotopes. And in the next lecture, where we are hoping to finish this particular module, we shall be discussing upon those characteristics of the isotopes only. So, thanks for your attention today, and let us just wait for some time for the next lecture. Thank you.